All right, in probability part 4, we're going to talk about sample space, which will give us the total number of combinations. And then over here, we're going to talk about combinations. There we are. Which will give us our outcomes of interest, right? The combinations and permutations. Good examples, sets of coins. If we want to know the probability of getting 4 tails out of 10 coins, then we need to know the sample space, how many total combinations are possible, and then how many combinations actually have our 4 tails, and then we can find the relative frequency. Let's look at some examples. First of all, we're talking about sample space first. Here's example 1. 5 dice are rolled. And what are all the possible outcomes of those 5 dice that get rolled simultaneously? Now, this is what's known as repetitive events. In which each event has the same number of individual outcomes. So in repetitive events, event 1 can produce m different outcomes. In this case, there are of course 6 outcomes for one event, one die roll. And then event 1 occurs n times. All right, so there are 5 dice, so there are 5 rolls. Another way of saying this is that n is the number of trials that are occurring. And so with repetitive events, that's relatively straightforward. Let's look at a tree diagram, which can be helpful. We can have our starting point, and then in the first event, event number 1, it's 1 die roll. There are 6 possible outcomes. 1, 2, 3. 1, 2, 3. And then each one of these will have 6 outcomes because this is the second die roll. And you can see that these get very complicated very quickly. And then, of course, we have... This is the first die roll, second die roll, third die roll. We go up to 5, and all of these are going to be branching. And all of these will be branching, and it's hard to draw them all in. But because it's repetitive, all the number of branches are all the same. So we have our total possible combinations or outcomes is just going to be each branch is 6, so it's going to be m to the n, which is, in this example is 6 to the 5th, right, which is 7,776 different outcomes by rolling 5 dice. And so this is a very useful relationship for repetitive events, fairly simple. It's just the number of outcomes per event raised to the number of trials. Now, if we don't have repetitive events, let's do example 2. Example 2. There we go, new page. Example 2. All right, let me write this out. So Luke can walk into one of 2 hotels. Each hotel has 8 floors. Each floor has 14 rooms. How many different paths can Luke take? So you can still use a tree diagram. Right? We have 2 hotels, so we're going to have 2 branches. Hotel 1, Hotel 2. Each hotel has 8 floors. So we're going to have 1, 2, 3, 4, 1, 2, 3, 4, 8 floors. And that's going to be true for both hotels. Each floor has 14 rooms. I'm not going to, of course, draw them all in, but you get the idea. There's going to be, each ending here has 14 other branches. Right, so there's going to be, 8 branches at this level and then 14 branches at the end. So total possible paths. So outcomes, I'll generalize. All right, now this is not repetitive because each event has different numbers of outcomes. So this is just going to be the product of all the outcomes. Now if we have m as the first number, so in this case m might be 2, n might be 8, it's the second branching, and p might be our 14. You just multiply them together, 2 times 8 times 14, and you get 224 different paths that Luke could take. And again, the total number of outcomes is what's important. When it's non-repetitive events, you're just multiplying them, which really is the same as repetitive events, because of course, like with the dice, you're just multiplying it by itself a certain number of times, so that's exponent. When you want to calculate probabilities, of course, relative frequencies would be the number of outcomes of interest over the total number of outcomes. We just did the total part, so that was the denominator. Total number of paths Luke can take, that would be the denominator of the relative frequency. Now to get the outcomes of interest, this is where we have combinations or permutations. And there's a slight difference. Here, permutations, the easiest way to differentiate is that the order matters, so that like in my earlier example of 4 tails out of 10 coins, it does matter what position the 4 tails are in. They would be counted separately, versus combinations where order does not matter. So again, in my discussion of 4 tails and 10 coins, it doesn't matter where the 4 tails are. It's just going to count when there are 4, without regard to what order those 4 might be in. So here's some examples I can write out. So here are the 2 examples. For the combinations example, coins, it's a really simple example. 8 coins are flipped. How many of all the possible outcomes contain 5 tails? So again, that would be a really clear probability of getting 5 tails out of 8 coins. Now, a permutation question is much more like this, where you have a class of 8 students, for example. 5 will be randomly selected to sit in the front row. How many different seating arrangements are there? So order now matters because different arrangements will be individually counted. So the way this is often written, this would be combinations. I'll give you, I guess I'll do the example first. So combinations, out of 8, we want 5. So this is often, 8 choose 5. The formula for this, we'll just go over the formula for a moment. N factorial over r factorial n minus r factorial. Now, a couple of points here. One is this whole factorial business, exclamation point. You may or may not have seen that before. So as a little review, if we wanted 5 factorial, well, that's 5 times 4 times 3 times 2 times 1. Right? It's that number times all of its preceding numbers down to 1. So, you know, 18 factorial would be 18 times 17 times 16, and I'm certainly not going to write all those out, but you get the idea, all the way down to 1. And so you can actually get quite large numbers with factorials. I should probably show you where that is on the TI-84. Hold on, I will bring that up. So over here we have our TI-84, and if we want to do 5 factorial, you go to the Math button, and over, you see the menus over here for probability. The fourth one is factorial. You can hit enter and you get that. There's a pretty good limit to factorials. When you get something like this, it gets pretty big pretty quickly. This e to the 15th, that's 6.40 times 10 raised to the 15th. If we do 25 factorial, we're getting up there. I can't remember. We get to the limit of the calculator fairly low. I think it was under 100. Yep. You get an overflow error. So you can kind of play around with it for a little while, and you can see where that overflow breakpoint is. But certainly 90 is overflow, and I think it's 70 or 80, somewhere around there. That's how you do factorial. So if we go back over here, don't really need these anymore. We have the n's and the r's. Right? So n is your total number. In this case, it would be 8. 5 would be the r. So that's your outcome of interest. So we have 8 factorial over 5 factorial, 8 minus 5 factorial. And so I could enter that into my calculator. 8 factorial divided by, make sure you use the parentheses, or it may give you the wrong answer. 5 factorial times, and of course 8 minus 5 is 3. 3 factorial is 3 times 2, so I don't see the use of using factorial when I could just do that. And we get 56. So so there are 56 combinations or 56 outcomes of 8 coins that contain 5 tails. Again, it doesn't matter where the tails are, you know, there's just 5 of them. Now the permutation one is if we have permutation of 8, 5 of 8. It's very similar, only it's missing one term. It doesn't have that r factorial out front in the denominator. So you can plug the numbers in. you can do it out, and this turns out to be 6,720. And I use the same numbers on purpose. Notice that this is 5 and 8, this is 5 and 8, because the results are really quite dramatically different, depending on whether order matters or not. Because if you are arranging 5 students out of a class of 8 in different orders, there are an awful lot of them. And, but here, if you're arranging, it's the same question actually as over here. If you had 5 tails out of 8 coins and order mattered, there would be the same number. It would be 6,720 of them. But if all we're interested in is the total 5 tails and we don't really care about the order, well, there's a lot fewer. There are a lot of repeats. So that reduces down to 56. And this 5 factorial in the denominator does that. Numerically, it reduces the value quite substantially. We also, these combinations and permutation functions can be found in the calculator also. I can show you where those are. So let's bring back our calculator. You should know what the formula is, but if we go over to math and probability, you'll notice actually up here we have NPR and NCR. All right, we have our N's and our R's and our C's. So the N always comes first, then the R. So what you actually need to do is we could go 8, math, probability, number 2, right, and then 5. And that should give us this 6,720 number, and it does. And of course, if you wanted to, you could do the combinations one, and it should give us our 56. A good way to get the difference between combinations and permutations is to look at it graphically. So what we'll do is maybe we'll split it widthwise. And up here we'll talk about combinations, and down here permutations. And we're going to use coins, but a smaller set, because of course we get very big numbers very quickly. And so we're going to do combinations, about 2 heads out of 3 coins. Right, so we have 3 coins, and we want to know all the possible combinations. Well, we can do a combinations tree. Have a starting point. And then the first coin can either be heads or tails, so that's coin 1. Then we can branch off from there and say, well, the first coin is a heads here, and the first coin is a tails here. The second coin can be a heads or a tails, a heads or a tails. And then each one of these will branch off. So that's the first 2 are both heads, and then the third one can either be a heads or a tails. And then with this one, the first 2 are both heads and tails, and the third is a heads or a tails. And we can keep doing this. And we could, of course, do this for any number of coins, but it would get really big really quick. You'll notice that this is 1 coin, this is 2 coins, all the possible combinations, and this of course is 3 coins. And how many are there total? 1, 2, 3, 4, 5, 6, 7, 8. So 8 total combinations. If we're looking for 2 heads out of the 3, well, we can say, look down and say, all right, there's 2 H's, there's 2 H's, and that looks like the only ones. So there are 3 combinations with 2 heads showing. Well, something like that. And to take the next step, what's the probability? Might as well talk about probability. All right, that's relative frequency. Nothing too new. All right, so 3 outcomes of interest out of a total of 8 possible outcomes, and there's our probability. It's no more complicated than that. So now let's talk about permutations. So we're going to use a similar question. We have 2 heads out of 3 coins. But now order matters, which means here's our 3 coins, coin 1, coin 2, and coin 3. They're individual now. We have to keep track of them individually. Like over here, this is tails, heads, tails. Is this tails from coin 1 or coin 3? We don't know. We don't really care. In combinations, you don't care which coin this is. It could be coin 1, coin 2, or coin 3. We don't really care which produced this T. But in permutations, we do. So we can do a similar branching, but it's going to be a little bit different. So the first coin, we're looking for 2 heads. Well, the first coin, the heads could be from coin 1. The heads could be from coin 2. Or the heads could be from coin 3. Right. Then from there, we can branch off and say, well, if the first heads came from coin 1, the second heads could come from coin 2 or from coin 3. And over here, if the first heads came from coin 2, then the second heads could come from coin 1 or from coin 3. And similarly down here, if the first heads came from coin 3, the second one could come from coin 1 or from coin 2. And so how many different permutations are there? Different arrangements of 2 heads from the 3 coins. There are 6 permutations. Right. For 2 heads showing out of 3 coins. So you can see that, the difference between permutations and combinations is permutations, each coin is individual. And we have to keep track of, is this coin 1 or coin 2 or coin 3? Where in combinations, we didn't care whether this H was from coin 1 or coin 2 or coin 3. This didn't matter to us. For most probability stuff, it's in fact the combinations that we'll use, although permutations will crop up every now and again. So I think that's will be it for this video. We'll pick this up in the next one.